Welcome to the lecture on controller design for TITO processes. TITO stands for to input to output. Also, we have got MIMO systems, where MIMO stands for multiple input, multiple output. Initially, we shall design a SISO controller for SISO process and then extend that to design of controller for TITO process. So, attempt will be made first to design a controller, series PID controller based on gain and phase margins. The transfer function shown over here, GCS, shows us a series form of PID controller, where we have got the proportional gain given as Kp and integral time constant given as Ti and derivative time constant given as Td. This is a series form of PID controllers, unlike the parallel form of PID controller, which can be given in the form of GCS equal to Kp 1 plus 1 upon TIS plus TDS. Why do we select series form of PID controller? It has got some benefit that we shall see after some time. Now, we shall assume the process, the SISO process, to have the transfer function Gs given in the form of K upon Ts plus 1 square with a delay given by e to the power minus theta s. So, this gives us a second order transfer function with delay. Assuming Td equal to T, the loop gain of the closed loop system can now be given as GGC j omega equal to K Kp times j omega Ti plus 1 times e to the power minus j omega theta upon j omega Ti times j omega T plus 1. Now, this loop gain is nothing but the open loop gain also. Sometimes we call this gain as the open loop gain of the closed loop system. The series form of controller enables us to make this choice Td equal to T, thereby cancelling 0 of the controller with 1 pole of the process transfer function. Let omega g and omega p be the gain crossover and phase crossover frequency. Then, as we know, at phase crossover frequency, the phase of the gain G G C j omega, the phase angle of the gain has to be minus pi. Now, this loop gain can be used, and we can find the angles from the loop gain as tan inverse omega p Ti given by this term minus omega p theta given by the delay term minus pi by 2 given by the pole at the origin minus tan inverse omega p t given by the pole j omega t plus 1, which is equal to minus pi now. At this phase crossover frequency, the loop phase will be minus 180 degree or minus pi. At the same phase crossover frequency, the gain of the loop G G C j omega p magnitude will be equal to K Kp times square root of omega p Ti square plus 1 upon omega p Ti root of omega p t square plus 1, which is nothing but same as inverse of the gain margin. We have taken A m as the gain margin, which is giving us the loop gain as 1 upon A m. So, these are the two equations, those are obtained using the phase crossover frequency point on the Nyquist diagram. Suppose we have got the Nyquist diagram and this becomes our Nyquist plot, then we have got the phase crossover point over here at the frequency omega p, which is nothing but the phase crossover frequency. So, this point gives us these two equations. Similarly, when the unity circle is considered and thus giving us the gain crossover frequency omega g at this point, giving us a gain crossover point, thus that will also result in two equations. And now, solving the 4 equations, set of equations will enable us to estimate the two unknown parameters of the controller K p and T I. We have already assumed T d to be T and again omega g and omega p. So, the 4 equations will give us estimate for K p T I, omega g, omega p. Let us see how can we simplify these expressions. The phase equation given in this form can be simplified further with the help of the assumption for arc tan function, tan inverse function. So, the tan inverse x can be given as pi x upon 4 when x is less than equal to 1, and tan inverse x becomes pi upon 2 minus pi upon 4 x for x is greater than 1. In our case, let us make some assumption again. Let omega p T I is greater than equal to 1 and omega p T is greater than or larger than 1. In that case, that helps us to write the equation in this form. The first term will give us pi upon 2 minus pi upon 4 omega p T I. The second term is written over here, then minus pi by 2 is here, then tan inverse omega p T can be written as minus pi upon 2 plus pi upon 4 omega p T, which is equal to minus pi. Collecting the terms, we get the simplified expression pi upon 2 times 1 minus 1 upon 2 omega p T I plus 1 upon 2 omega p T equal to omega p theta. So, we get one simplified expression using the information from the phase crossover point. Similarly, the gain at the phase crossover frequency can be expressed as k k p times root of omega p T I square plus 1 divided by omega p T I root of omega p T square plus 1 equal to 1 upon A m, the gain margin. This is same as 1 upon the gain margin, which is nothing but A m in our case. Already we have made this assumption that omega p T I is greater than 1 and omega p T is greater than 1. That assumption will help us to express the equation in a simplified form as k k p omega p T I upon omega p T I omega p T equal to 1 upon A m, that we have got here, which upon simplification further gives us omega p equal to k K p A m upon T, and this is the second equation we get. So, we have got an expression for the phase crossover frequency, which is given as k Kp Am upon T. Let us make use of the other information we get from the Nyquist diagram, that is what happens at the gain crossover points. So, gain crossover point will result in two equations, one equation shown over here and the other one is the equation relating the phase margin. Now, at gain crossover frequency, the loop gain can be expressed as k Kp times root of omega g T I square plus 1 divided by omega g T I root of omega g T square plus 1 equal to 1, because as we know at the gain crossover frequency, the loop gain is 1. Making the use of the assumption that omega g T I is larger than 1 and omega g T is larger than 1, this expression gives us now k Kp omega g T I upon omega g T I omega g T equal to 1, which further gives us omega g equal to k Kp upon T. So, let us give this equation number 3 for this equation. Now, using the phase at the gain crossover frequency, the loop phase at the gain crossover frequency will result in the gain phase margin of the system. So, defining the phase margin of the system, which is given by the symbol phi m, equal to pi plus tan inverse omega g T I minus omega g theta minus pi by 2 minus tan inverse omega g T. This phase equation can easily be obtained using the expression loop gain for the system. Since arctan functions are to be approximated to get simplified expression for these, we have to make use of the same assumption we have made earlier. When tan inverse x equal to pi x by 4 for x is less than 1 and equal to pi by 2 minus pi upon 4 x for x is greater than 1, then the phase margin expression gives us pi upon 2 minus pi upon 4 omega g T I minus omega g theta minus pi by 2 minus pi by 2 plus pi upon 4 omega g T equal to phi m minus pi. This is what we are getting from the expression we have obtained earlier for the phase margin, considering the gain crossover point. Now, this expression can further be simplified and written in the form of pi upon 4 omega g T I plus omega g theta minus pi upon 4 omega g T equal to pi by 2 minus phi m, giving us equation number 4. Now, ratio of equation 1 and equation 4 gives us omega p upon omega g equal to pi by 2 minus phi m minus omega g theta upon pi by 2 minus omega p theta. Now, substituting omega p and omega g in this expression enables us to write an expression for k Kp in terms of the gain margin, phase margin and the plant parameters t and theta. So, using this expression along with the expression for omega g and omega p, we see omega g equal to k k p upon t and omega p equal to k k p a m upon t. So, using those two expressions, it is possible to find the expression for k k p as given over there. So, k k p equal to pi upon 2 times a m minus 1 plus phi m upon a m square minus 1 times t upon theta. So, what we get from this expression? This expression, if you look at carefully, has got the unknowns k p. So, k p is the only unknown, since k, t, theta are known. K, t, theta are the parameters of the process model. Thus, those are known to us, and a m and phi m are the gain and phase margins defined by the user. Thus, a m and phi m are also known a priori. This expression helps us to estimate the proportional gain k p. Similarly, attempt will be made to find one more expression to obtain the remaining parameter of the series PID controller. Expression 1, equation 1 is known to us, which is nothing but pi upon 2 times 1 minus 1 upon 2 omega p t I plus 1 upon 2 omega p t equal to omega p theta. Again, substituting the expressions for omega p, one can simplify the above expression and obtain the expression for t I, the unknown constant or unknown time constant associated with the series PID controller, in the form of t I equal to pi t upon pi times 1 plus 2 k k p a m minus 4 k square k p square a m square theta upon t. So, this expression can be used to estimate the unknown parameter t I. Let us look at the right hand side of equation 6. What are the knowns and unknowns over there? In the right half, we can see that k, t and theta, these are known to us, these are the parameters of the process model. A m and phi m is not used here, or a m and phi m are user defined, therefore, these are also known to us. Then, using this equation 6, expression 6, one can easily estimate the unknown parameter t I. Thus, one is able to estimate all the unknown parameters of the series PID controller using 5 and 6. So, the control design method can be summarized as given below. Given k, theta and t, which are nothing but the process model parameters, we need to choose the phase margin and gain margins for the closed loop system. Then the proportional gain of series PID controller can be estimated using equation 5. So, using equation 5, K p can be estimated. Similarly, equation 6 can be used for estimating the integral time constant of the series PID controller. Thus, the parameters of the series PID controllers K p, T I and TD are estimated using the gain and phase margins. Now, TD is already known to us, which is nothing but equal to the time constant of the process model. We shall make use of this phase and gain margin method for designing controllers for a TITO system. Before that, let us see how the control loop performs with the design values of the Kp, Ti and Tt. Let us assume the process dynamics to have the form of Gs equal to e to the power minus 2s upon 8s plus 1 square. So, we have got a process, second order process with repeated poles located at minus 1 upon 8 and with a delay of 2 seconds. Now, using k equal to 1, t equal to 8 seconds and theta equal to 2 seconds, the parameters of the series PID controller can be obtained with the assumption that with the choices that phase margin of the loop is 45 degree and gain margin is 3. So, using phase margin and gain margin values and k, t, theta, Kp, Ti are estimated. Kp is found to be 1.9635 using equation 5. So, using equation 5, Kp can easily be obtained. Similarly, the integral time constant Ti is estimated to be 4.6075 for this case for the choices of given phase and gain margins, and Td equal to 8 equal to T. So, we have got series PID controller parameters given over here with the choices of phase and gain margins of 45 degree and 3 respectively. Now, the integral controller is implemented over here. The derivative controller has a derivative time constant of 8 seconds and the proportional gain is given by a gain of 1.9635. When this simulation diagram is used, simulation result gives us a closed loop response of this form. We have also assumed a step load disturbance of magnitude 0.5 occurring at time t equal to 60 seconds. So, a step load disturbance occurs over here, which is of magnitude 0.5 at time t equal to 60 seconds. Then the response obtained is of this form. If we will carefully look the response, we have got a time response which is giving about 25% overshoot and a settling time of about 30 seconds, and we have got a disturbance rejection also. It ultimately settles down. If I draw the reference line correctly, it goes in that form. So, although the overshoot is a bit higher, the settling time is higher, the rise time is very good. The rise time is approximately of the magnitude 2 seconds or so. So, we have got a very good rise time for the closed loop response. So, the closed loop response is found to be quite satisfactory as far as performance of the closed loop to plant or process parameter variations are concerned, because we are designing robust controller for the system based on gain and phase margins. Therefore, we may have a bit higher overshoot and settling time, but the overall response is always satisfactory for variations in the process parameters. Now, attempt will be made to make use of this technique for designing PID controller for 2 input 2 output system. What a 2 input 2 output system or what a multiple input multiple output system is. As for example, let us consider a situation, an office which has got 2 chambers and we need to maintain different temperatures in the 2 chambers. Suppose one chamber has to have 30 degree centigrade and the other at 25 degree centigrade. In that case, one has to employ 2 sensors for the chambers. Therefore, we will have 2 outputs for the system. The outputs are obtained from the sensors. Now, since we have to maintain different temperatures in the chambers, therefore, cool airs are to be pumped in with the help of dogs. Then we have got 2 dogs for the 2 chambers, thus giving us 2 inputs to the system. Therefore, the office room dynamics can be regarded as a 2 input 2 output system, where we have got 2 inputs and 2 outputs. Similarly, we have got multiple input and multiple output in a real time in industrial environments. Now, how we can make use of the phase and gain margin based controller design for 2 input 2 output system, that we shall see now. So, a 2 input 2 output system is different from a single input single output system in the sense that there is no coupling present in the SISO process, whereas there are couplings interactions between the loops of a TITO system. That is the only difference we have between the TITO system or TITO process and a SISO process. So, the MIMO or SISO processes have got spatial coupling. Now, let us see the block diagram representation of a 2 input 2 output system. So, we have got one input over here, another input over here, thus giving us 2 inputs for the system and we have got 2 outputs. Now, the 2 input 2 output system has got interactions also given in this fashion. That is why there are 4 blocks representing the dynamics of a TITO system, which has got interactions present between the loops. Now, when 2 PID controllers are employed for controlling the TITO process, we have got 2 loops. Suppose this is loop 1 and this is the loop 2. So, the 2 loops will give us dynamics in such a manner that the dynamics are affecting each other. There is enough loop interaction between the individual closed loop systems. So, the controller can be designed provided the dynamics of the TITO processes is obtained in some convenient form. Is it possible to obtain the dynamics of a TITO or MIMO system in some convenient form? Yes, it is possible. So, employing model identification techniques, it is possible to obtain the dynamics of TITO system in some convenient form. In the block diagram, what else we see apart from the 2 series controllers GC1S and GC2S, we have got load disturbances given by L1 and L2, and noise disturbances given by M1 and M2. Now, the dynamics of the TITO process is assumed to have the form GMS equal to GM1S and GM2S in diagonal of this transfer matrix. So, the TITO process dynamics is given by a transfer function matrix often known as transfer matrix given as GMS equal to GM1S 0 0 GM2S. Thus, we get one diagonal transfer function matrix for the TITO system. This form of transfer function representation helps us to design conveniently controllers for the system. Now, the controller dynamics is also given in a similar fashion. We have got controller 1 and controller 2 present in this fashion. What benefit one gets from here? This sort of representation of the plant dynamics and the controller dynamics help us to design two controllers in a convenient manner, in the sense that as if there is no loop interaction between the two loops of the TITO system, one has to tune the parameters of the series PID controller based on the dynamics we have obtained in this form. Now, the controller GC1S will be designed based on the dynamics of GM1S only. Similarly, the controller parameters of GC2, GCL2 or GC2S will be obtained purely based on the parameters of GM2S, thus giving us freedom to design the two series PID controllers in a way we have designed for SISO processes. Now, after assuming the form of the controllers and the process dynamics in the convenient forms, let us assume the dynamics of the processes to be available in the second order plus delay transfer function form. What is this I stands for? I stands for I varies from 1 to 2. So, when I equal to 1, we get a process transfer function which is given as GM1S is equal to K1 e to the power minus D1S upon T1S plus 1 square. That means, GM1S is given as K1 e to the power minus D1S upon T1S plus 1 square. So, this is the dynamics of the process transfer function. Similarly, GM2S can be expressed as K2 e to the power minus D2S upon T2S plus 1 square. What are those K1, K2, T1, T2, D1, D2? Those are the steady state gains, time delays and time constants of the process models. So, K1, K2 are the static gains, D1, D2 are the time delays and T1, T2 are the time constants of the TITO process model. Similarly, the controller dynamics now can be obtained in the form of GCLIS is equal to KCI times 1 plus 1 upon TIS times 1 plus TDIS, thus giving us two series PID controllers when I assumes values like 1 and 2. So, when I equal to 1, I get a series PID controller with parameters KC1, TI1 and TD1, whereas when I equal to 2, the controller parameters become KC2, TI2 and TD2. Now, attempt will be made to estimate the unknowns, estimate the controller parameters KC1, KC2, TI1, TI2, TD1 and TD2. So, once these values are estimated using the phase and gain margin techniques, then the controllers have been designed for the TITO process. Like the earlier case, let us make this assumption with the choice of TDI equal to TI, then the loop transfer functions can be given as GMI GCLI j omega is equal to KI KCI e to the power minus j omega di upon j omega ti plus 1 times 1 plus 1 upon j omega ti I. Again we shall make use of the phase crossover point and the gain crossover point and ensuing informations from those points to design the controller parameters. The phase crossover point gives us equations like the magnitude of the loop gain at phase crossover frequencies omega pi will be equal to 1 upon AMI, where AM1 and AM2 are the gain margins of the two loops, gain margins of both the loops. At the phase crossover frequency, the net phase angle contributed by the loops will be equal to minus pi, which can be put in the form of pi plus angle of GMI GCLI j omega pi equal to 0. Similarly, the gain crossover point enables us to obtain two more equations in the form of magnitude of loop gain GMI GCLI j omega gi is equal to 1 and pi plus argument of GMI GCLI j omega gi is equal to phi mi, where phi m1 and phi m2 are the phase margins of the loop. Thus, what are known and what are unknown in these equations? We have obtained a set of 4 equations. Now, the 4 equations can be solved to estimate 4 unknowns. What are those 4 unknowns? Definitely, unless the number of equations and number of unknowns are equal, we may not get unique solutions from the equations. So, the 4 unknowns are nothing but omega p1, omega p2, or I can say omega pi rather, omega pi, omega gi and phi mi ami. So, we have got 2 unknowns like this, and these 2 variables are known to us in the sense that these are user defined. Then the unknowns, 2 more unknowns like KCI, no, we have put the gains as KC. Okay. So, thus KCI and TI I are the two more unknowns. So, the unknowns are omega pi, omega gi, kci and tii. These are the four unknowns and we have got four equations enabling us to estimate unique values for the unknowns kci and tii, the unknowns of the series PID controllers. Using the phase and gain margin criteria, the equations further can be simplified in the form of equations giving us Ki Kci equal to omega gi tii square root of omega gi square ti square plus 1 upon omega gi square tii square plus 1. AMI Ki Kci equal to omega pi tii square root of omega pi square ti square plus 1 upon omega pi square tii square plus 1, and the phase equations can be written in the form of pi upon 2 plus tan inverse omega gi tii minus tan inverse omega gi ti minus di omega gi equal to phi mi, and pi by 2 plus tan inverse omega pi tii minus tan inverse omega pi ti minus di omega pi equal to 0. So, these are the set of equations we have obtained from the four inequalities or equations one can obtain using the phase and gain crossover points. Those four equations are to be simplified now with the assumption of the arctan function tan inverse x given in this form. For that, let us assume that omega gi ti is greater than 1, omega gi tii is very large compared to 1, and omega pi ti is very large than 1, and finally, omega pi tii is large compared to 1. So, when these four assumptions are met and the arctan function is used, then the four equations we have obtained from the phase and gain crossover points can further be written in the form of Ki Kci is equal to omega gi ti, AMI Ki Kci equal to omega pi ti. Keep in mind AMI is nothing but the gain margins of the loop, and pi upon 2 minus pi upon 4 omega gi tii plus pi upon 4 omega gi ti minus di omega gi equal to phi mi, where phi mi stands for the phase margins of the phase margins of the loop, phase margins of the loop. Now, the last equation can be put in the form of pi upon 2 minus pi upon 4 omega pi tii plus pi upon 4 omega pi ti minus di omega pi equal to 0. Simplification of the four equations give us expressions for the unknowns Kci tii as Kci equal to C1 upon Ki times Ti upon D, and Tii equal to Ti upon 1 plus C2 times Ti upon D, and we have already made this assumption at the beginning that Td equal to Ti. So, we have got the expressions for the unknown KCI and TII in terms of all the known parameters. What are those known parameters? We know Ki, we know Ti and we know Di. Actually, this will be Di. So, these are nothing but the known parameters, since we know the transfer function models of individual loops now. Now, the C1 and C2 in the expressions are given. These are the two constants given in the form of C1 equal to 2 phi m plus pi times a m minus 1 upon 2 times a m square minus 1, and the second constant C2 is given as 2 a m C1 times 1 minus 2 a m C1 upon pi. So, choose the phase and gain margins for your loops a m and phi m. Once the phase and gain margins are chosen for the loops, then C1 and C2 constants are obtained. Using C1 and C2 and the knowns Ki, Ti, Di, it is not difficult to estimate the unknowns KCI, Tii. Thus, we obtain the thus we estimate the unknown controller parameters using the final expressions given here. So, once the controller parameters have been obtained, then you have got the two series PID controller for the TITO process. Now, this is how we have extended the controller design method technique to TITO process. Now, we shall see how the control loops are performing. For the simulation study, let us assume the plant dynamics to have the transfer function 1 upon s plus 1, 2 s plus 1 square, 0.5 s plus 1 with interactions also. The original plant dynamics can be modeled in the convenient form given over here. So, the original plant dynamics has been modeled as GMS equal to given by 1 GM1 S 0 0 GM2 S. Next, choosing the phase margins of 2 and gain margins of 45 degree for both the loops, the controller parameters are designed in such a way that we have got two series PID controller for the TITO process given in the form of GCL1S equal to 10.14 times 1 plus 1 upon 3.76 S times 1 plus 0.94 S, and GCL2S equal to 12.4 times 1 plus 1 upon 3.52 S times 1 plus 0.88 S. So, we have got here KC1, this value is the TI1 and this is our TD1. Similarly, we have got KC2, TI2 and TD2. So, employing the controllers, we get a time response of this form, where Y1 gives us the output of the first loop L1. So, this is the output of loop 1 and this is the output of loop 2. We can say that since we have got a TITO process, we have got two outputs for the process given as Y1 and Y2 T. So, the two outputs are found to be satisfactory in spite of interaction among the loops or interaction between the loops in the TITO process. The output response is found to be quite satisfactory. The lesson can be summarized in this fashion. We have designed gain and phase margin based series PID controller for a SISO process initially, and the design technique, the controller design technique can be extended to TITO process with ease, provided the TITO process dynamics is available in diagonal transfer matrix form. Simulation diagrams and simulation results show us that it is possible to obtain satisfactory closed loop performances from the TITO process using control design using phase and gain margin. Points to ponder. First point, if somebody asks why do we use approximation for the tan inverse function. The arctan function has been approximated for each in analysis. If the approximation is not used, then the set of 4 equations are to be solved simultaneously. Since those equations are nonlinear equations, therefore, solution may or may not converge, or with proper choice of initial conditions only the solutions may converge. So, there are risks in solving the set of nonlinear equations. To avoid that, to get explicit expressions for the plant, for the given plant, to obtain explicit expressions for the controller parameters, it is better to make assumptions. If the second question goes like this, why the transfer function matrix is given in diagonal form? Not necessarily the dynamics has to be made available in the diagonal transfer function form. If it is not so, in that case some decoupling technique has to be made use to design effective controller for the TITO process. Lastly, if the question is like this, that are there any other method available to design SISO controllers for a TITO system? Yes, one can use decouplers, one can use some other technique to reduce loop interactions and design controllers for a TITO system. That is all in this lecture.